Alright, so today is going to be a brand new topic. It's something called radians. You've probably heard of the term radian before because in your calculator we've always told you to set your calculator in degree mode during trigonometry. And now you're going to have to be able to set it in radian mode, which was the other option that you probably have read and heard about. What a radian is just another way of measuring angles. So the actual definition is here on the board. The big thing that you need to know is just that a radian is a measurement from the center of a circle here to the outer edge, where the circumference that you've created in that angle, so this red line all the way across the top, is the exact same length as the radius from the center to the edge. You're not going to have to know the definition of a radian, but sometimes people just like to know what it is that creates a radian. So that's how we measure it. It's an angle that creates a length that's the exact same as the arc length. And they even told you down here that 1 radian is approximately 57.3 degrees. You don't need to know that at all. Some things that you do want to know about radians is that 1 pi equals 180 degrees. 2 pi equals 360 degrees. So that means pi would be half the circle, and 2 pi would be 1 full rotation of an angle around the circle. And the first thing we're going to do is we're going to convert radians and degrees into each other. To do that, we use this formula. I don't actually use this formula. That's the formula you're going to see in a lot of places if you look at any other references. I like to use that formula but flip it. So instead of having it 180 over 40 equals pi over x, I would go 40 over 180 equals x over pi. The numbers that go on the top, here, those are the numbers you either want to convert or want to find. And the numbers that go on the bottom are always the exact same thing. They're pi and 180. The reason you can do that is you're just setting up a ratio. Where you're saying if 40 over 180 should be the exact same ratio of whatever the radians is over pi, because 180 and pi are the same measurement on an actual circle. So I use this formula. It's easier, so I like to put my converting and what I want on the top. I put the 180 and the pi on the bottom. So if I was to actually do this, clean that up a little bit. If I wanted to convert 40 degrees and go 40 over 180 equals some number of radians, x over pi. I need to get x by itself, so I times both sides by pi. And then I'm just going to put that in my calculator. So your pi button on your calculator, remember it's the right above the division sign. So you go second, and then I call that button the little hat button. It's right above the division sign. So you go pi times 40, then divide by 180, and I get that my approximate value would be 0.698 radians. The exact value, I don't want to multiply by pi. So I'm going to just take this fraction of 40 over 180. I'm going to put that in my calculator. I'm going to math bracket to turn it into 2 over 9. And then I'm going to leave the pi on top beside the 2. So I would say it's 2 pi over 9 would be my exact value. Alright, we're going to try that one. So we're going to go the other way around. We're going to convert 5 pi over 6 radians into degrees. To do that, I put what I want to convert on the top. So I have 5 pi over 6, and then divide by pi equals, I don't know, over 180. So I'm converting 5 pi over 6 into some measurement of degrees. To solve that thing, what you're going to do is you're going to have to multiply the 180 to the other side. So multiply both sides by 180. then punch the whole thing in your calculator. To do that, you might want to break it into chunks. So I would just go like 5 pi, hit enter, divide that by 6, hit enter. Now I know that 5 pi over 6 equals 2.6178. I'm going to times that by 180, and then divide that by pi. And my final answer is going to be 150 degrees. We're going to do some practice converting these things. It usually takes a few times before you actually start to feel comfortable with it, but it is quite easy once you get going with it. So we're going to convert all of these degrees into radians. So you want to convert 30 degrees into radians. So we want 30 to equal some number of radians. You have to create your ratio, so it's 30 over 180 equals x over pi. We're going to have to multiply pi to the other side. So times by pi, times by pi. We're going to write this as an exact value because that's how we normally write it. So I go 30 divided by 180, math frac that. That means it's 1 over 6. So I would call this 1 pi over 6. And you don't have to write the number 1. I'm going to put it there just so you see it. But the 30 over 180 simplifies to be 1 over 6. And then you multiply it by pi. If we try another one, we have 45. We want to convert that into some radians. So 45 over 180 equals x over pi, because 180 and pi are the same measurement. I'm going to times pi on both sides. I'm going to simplify 45 divided by 180 by putting it in my calculator and math fracking it. It's equal to 1 over 4. So that means my final answer is pi divided by 4. It really is pi times 1 divided by 4. But the times by 1, you don't need to write that in there. We'll do one more together, then you'll do the 3 on your own, and I'll put the answers on the board. So if you want to convert 90 degrees into radians, you go 90 over 180 equals some number of radians divided by pi. I'm going to multiply pi to the other side. 90 divided by 180 is 1/2. Multiplied by pi. Again, we simplify that to just be pi over 2. That would be my answer as an exact value. Okay, try the other 3 on your own. I'll put the answers on the board. Okay, so the answers are now on the board. 180 converts to just be pi. 225 converts to be 5 pi over 4. And 360 converts to be exactly 2 pi. If you wrote the E225, it's 5 pi, say 5 over 4 times pi. We just convert that thing into 5 pi over 4. We multiply the numerators together so that it's in a nice single fraction of that. Alright, we're going to convert the other way. So we're going to convert from radians into degrees. This is usually a little bit trickier just because the fractions get a little uglier. But on the plus side, if you get good with putting it in your calculator, it works out nice. So we're going to convert radians into degrees. I have pi radians. I want to convert it into some number of degrees. I'm not sure what it is. On the bottom, I always put pi and 180. Notice that 180 always goes under whichever one your degrees is, and pi always goes under whichever one your radians is. We're then going to solve this thing. So pi divided by pi cancels out. Times by 180 to the other side. And your answer is 180 equals x. It's 180 degrees. If we try another one, we have pi over 2. We want to convert it into some number of degrees. That number of degrees is going to be divided by 180. The pi over 2 is going to be divided by pi. You're going to multiply pi, or sorry, 180 to the other side. So multiply 180. Cancel. Multiply by 180. Again, if I were you, I would put this in my calculator nice and slow. So I would go pi divided by 2, hit enter. Then I would divide that by pi. And then I times that by 180. So that my answer is 90 equals x. So what I'm doing is I'm putting pi over 2 in my calculator, then dividing it by pi, and then multiplying it by the 180. And that's how I'm getting my answers. The last one we're going to do together, we have 4 pi divided by pi equals some number of degrees over 180. You're going to multiply the 180 to the other side. You put it on your calculator, so 4 times pi divided by pi times 180, and your answer is 720 degrees. Do the other 3 on your own and see what you get for answers. Alright, so your other 3 answers are on the board. The third one's a little interesting because it's negative. So if it's negative, that means when you were measuring it on your Cartesian plane, positive angles, we talked about it, they go this way, counterclockwise. If it's a negative angle, it means you went 420 degrees the other way, which is a little bit different. If you don't remember that, that's from the other lesson, 6.2. No, 6.3. Alright, the next thing we're going to investigate. We're going to investigate something called special triangles. These special triangles are going to link into something called a unit circle, which we'll do in the next slide. The unit circle you will always be given to you in this class, but next year you'll have to make it completely on your own. So you will have to memorize it next year. Alright, special triangles. Special triangles are triangles that have hypotenuses of 1. So you'll notice we've drawn 3 special triangles, all with hypotenuses of 1. And you'll notice we have 3 different angles. We have 30, 45, and 60 as my 3 other angles. Those are my special triangle angles, and my special triangle hypotenuses are as well. We're going to try to calculate the other 2 sides. So in our case, we call it the opposite and the adjacent. We're going to solve the opposite first in this first one. So if I wanted to solve the opposite, I would go sine of 30 equals opposite over hypotenuse, which is just 1. Dividing by 1 is pretty much useless. So if I just go sine 30 in my calculator, and my calculator is in degree mode, I end up finding out that 0.5 equals my opposite. I'm going to write that up here in the triangle, but instead of 0.5, I'm going to put 1 divided by 2. We like fractions a little bit more. To solve for your adjacent side, we could do the same thing. We could do like SOHCAHTOA, but I'm going to do something different because I want an exact value. And so I know that using sine, cosine, tangent, often I end up with crazy irrational decimals. So instead, I'm going to do Pythagorean Theorem using 1 and 1/2. Our formula for that, which we did in day 1 of this unit, would be the adjacent will equal the square root of 1 squared minus 1/2 squared. So if we were to put this into our calculators, that means our adjacent equals the square root. And if you go 1 squared minus 1 divided by 2 squared, you'll get 3 over, it is 0.75, but we change that into fractions, so 3 over 4. And if you remember your Unit 1 lesson, we don't write fractions under root signs, so this would actually be the square root of 3 over the square root of 4, which is just 2. So we're going to call this side root 3 over 2. So that means in our special triangle where the angle is 30 degrees, we're going to have an opposite of 1/2 and an adjacent of root 3 over 2. Alright, our next special triangle is our 45-degree triangle. To solve that thing, we're going to use Pythagorean Theorem again, but we're going to also utilize some information we know. We know that all 3 triangles have to equal 180. That means if we went 180 minus 45 minus 90, the third angle in this triangle has to be 45. If both angles are the same thing, that means both these sides should be the same thing. They have to be the same measurement. This is called an isosceles triangle, where you have two sides the same and one side different. Now, to calculate those sides, I could have used SOHCAHTOA or anything like that, but it's going to give me decimals, and I don't like decimals. I want an exact value. So to get an exact value, I'm going to use Pythagorean Theorem. So I know that x squared plus x squared is going to equal 1 squared. And I'm going to simplify this a little bit. So x squared plus x squared is 2x squared. 1 squared is just 1. They divide both sides by 2, and x squared equals a half. They square root both sides, so x equals root 1 over root 2. Remember our little fraction, so if you square root something, you're square rooting the top and you're square rooting the bottom. So by square rooting, I square the top and I square the bottom. The square root of 1 is just 1, so I leave it like that. Our final step, this thing is not a good enough answer because it's got a root sign on the bottom, which we did do some review on. So you need to rationalize your denominator, which means you need to multiply the top and the bottom by root 2. When you do that, you end up with root 2 over 2. And that'll be our answer for both sides. Root 2 over 2, root 2 over 2. So for our special triangle where the hypotenuse is 1 and the angle is 45, we end up getting root 2 over 2 as our two sides. Alright, the third special triangle. The third special triangle that we have is a 60-degree triangle. We could also put the special triangles beside each other. And if we did that, so if we had two 60-degree triangles, what we end up creating is an equilateral triangle. Which means this entire distance right here would have to be 1. Because an equilateral triangle has all sides the same. So if we wanted to focus in on just one of our triangles, let's look at just one of our triangles with angle 60. We have to know that this distance right here is 1/2 of 1, so it's 1 over 2. Right? The whole bottom had to be 1 if you were to have put a triangle right next to it. If we cut that in half, that means that it must be 1/2. And if we look at our original triangle, we already know that if one side is 1/2 and one side is 1, the other side is going to be root 3 over 2. So that means your special triangle, look at this, that's 60 degrees, 1, root 3 over 2, and 1/2. And we're using that more through like intuition and thinking about the other triangles we already know and how that works. Alright, how these special triangles help us out is we can look at our primary trig ratios. Remember, our primary trig ratios are sine, cos, and tan. You want just to know opposite over hypotenuse. You want to know adjacent divided by hypotenuse. And you want to know opposite divided by adjacent. So by looking at our special triangles, we remember all of these lengths. This is from the slide before, so if you forgot that, you could look back in the last slide and just fill this out with me. There we go. So I've drawn in my special triangles. We're going to do sine, cos, and tan for each one of these things. So if I did sine on the 30-degree triangle, sine would be opposite, which is root 3 over 2, divided by 1, which is my hypotenuse. Anything divided by 1 is the exact same thing. So it's just root 3 over 2. And you're going to notice that sine for my root 45 is going to, or my angle 5 is going to be the same idea. It's going to be my opposite, which is root 2 over 2, divided by 1, which is just root 2 over 2. And on our last one, the same thing happens. It's root 3 over 2 divided by, we got our special triangle drawn first. 1/2, and it's root 3 over 2 like that. My apologies. So this means this is 1 over 2. Opposite divided by hypotenuse. And this over here is root 3 over 2. What you notice is that your sine value just gave you your opposite on these special triangles every single time. So if I went sine of any angle on those special triangles, I automatically know what my opposite side is. The reason that's happening is because your hypotenuse is equal to 1. And if your hypotenuse is equal to 1, sine is just going to give you that value, the opposite side. Alternatively, if you do cos, it's going to be adjacent divided by 1. And if you're divided by 1, you're going to get the same thing. So this one's going to be root 3 over 2. This one's going to be root 2 over 2. And this one's going to be 1. All because I'm dividing by 1 every single time when I do my cos ratio. The tangent one is a little bit harder. The reason the tangent one is a little bit harder is tangent is opposite divided by adjacent, so I'm not dividing by 1 anymore. So opposite divided by adjacent for my 30-degree triangle would be 1/2 divided by root 3 over 2. You're going to have to simplify that thing. So you have a fraction divided by a fraction. You're going to have to do some kissing and some flipping. So I'm just going to write that on the top and kiss and flip it up here. So if I had 1/2 divided by root 3 over 2. If I kiss and flip that thing, it becomes 1 over 2 times 2 over root 3. Those will cancel. Equals 1 over root 3. You're going to have to rationalize that, right? It's not allowed to stay like that. So that thing's going to change to be root 3 over 3. The next one, the 45-degree triangle, you're going to do opposite divided by adjacent. If we look at this triangle, we notice that opposite is root 2 over 2 and adjacent is root 2 over 2. And anything divided by itself is just 1. So the answer to that would literally just be 1. Our last triangle, if we did opposite divided by adjacent, this time it's root 3 over 2 divided by 1/2. You're going to do the same thing. You're going to kiss and flip that. You can do it on the side if you want. When you kiss and flip that, it just equals root 3. The tangent ratios are definitely the harder ones. It's also ones we don't work with very often. We use our sine and cos a lot. The reason we use these a lot is these special triangles create something called a unit circle. And I'm just going to take a minute now to remind you that you do not have to have the unit circle memorized, which means you don't have to have those special triangles memorized. It's just good to see where they came from and how we're actually calculating these side lengths. But if all that calculating of those special triangles confused you, like that's a-okay. Because you're going to have this unit circle given to you, and that's all we use the special triangles for, is to create that unit circle. Alright, the unit circle is a special circle with radius 1. So that means anywhere from the center to the outer edge would be a distance of 1. That means if you were to create some triangles in here with standard position angles of 30 degrees, 45 degrees, and 60 degrees, you would have our 3 special triangles. Our one triangle would be right here with 30 degrees. Our other one would be right here with angle 45 degrees. And our last special triangle would be all the way here. That's 60 degrees. So you can see the three special triangles there. It's kind of messy, but you should be able to see them. I'm going to erase them. What we're going to do is talk about the terminal points that happen. So when I'm at an angle of 30, there's a point right there. That point, if you remember, are x and y values. And if you were to create your special triangle, that means x and y are now your opposite and adjacent sides. So I know that my point out here is at whatever my special triangle told me my opposites and my adjacents were. So according to my special triangle, my y value should be a half, and my x value should be root 3 over 2. So 1/2 and root 3 over 2. Try your best to draw small, because this is going to get quite convoluted. I got that backwards again. Sorry. The 30 degrees in here. Just so for reference sake. And I do have that backwards. Again, I read that special triangle backwards. Very small. Maybe some dyslexia or something. Who knows? It's root 3 over 2. If you looked at the next triangle, that's a special triangle up here. That's our 45-degree triangle. That was root 2 over 2 as our adjacent side, and our opposite side would be root 2 over 2. If you look at your special triangle of 60, your adjacent side, which would be your x value, would be 1/2. And then root 3 over 2 would be your opposite value. The other one that we're going to talk about is if you went straight up to 90 degrees up here, that means you wouldn't have a triangle really. What you have is a radius of 1. So that means your x value is 0 and your y value is 1. Those are sometimes hard ones to do, but you just have to think about them and know that if you're on the unit circle, it means your radius is 1. And if I went straight up, that means I haven't gone left or right, so I don't have an x value. So x has to be 0, y has to be 1. I'm going to fill out the rest of this unit circle. Notice that you actually have special triangles in every quadrant. So if we look over here in quadrant 2, we have another special triangle. And it's the exact same special triangle as this one over here that was 60. It's just now it's in a different area, right? It's in a different quadrant. But the points are going to be the exact same because the triangle is the same. So the distances have to be the same. The difference is now I have -1/2, comma, root 3 over 2. Because I had to go to the left instead of to the right of the origin. If we did the other one, it would be the same idea. So it would be this triangle that used to be 45. Now it's in the other quadrant, so we would have -root 2 over 2, comma, root 2 over 2. And our third point out here would be -root 3 over 2, comma, 1 over 2. Right, it's the same as the points in the first quadrant, except the x values are negatives now because it went to the left instead of to the right. We could do the same thing in quadrant 3. Oh, sorry, I missed our 180. This 180 point over there, now I've gone -1 to the left and 0 up. So that would be my point at 180. I can do the same thing over here now. I'm down in this quadrant. That would be my 30-degree special triangle. So if I'm looking at it, this triangle should look the same as the one in the 30 degrees. It does look the exact same. So the point should be the exact same, except now it's going to be -root 3 over 2, and negative 1 half. Like that. The other 2 points are going to be the same thing. So you're going to have 240 degrees out here. That thing's going to be negative root 2 over 2, comma negative root 2 over 2, because it's actually the same triangle as the 45-degree triangle. If you look at the reference angle of 225, it would be 45 degrees. Sorry, 225. It's in the that one. 240 degrees out here, that would be your next point. And that thing's going to be negative 1 half, comma, negative root 3 over 2. And I will give you a unit circle handout so that you can kind of see what this looks like in a nice little piece of paper. Because I know your pictures are going to be a little bit crazy. So once you're done this lesson, you can grab the unit circle from the front of the class. Your last point over here at 270, that means I went 0 and then down 1 because my radius is 1, so that must mean I went down a distance of 1. Your other 3 values we're going to fill out real quick, so it'd be this guy would be 1 half, and then negative root 3 over 2. It's got to be negative root 3 over 2 because we went down. This guy's going to be positive root 2 over 2, comma, negative root 2 over 2. And then this guy up here is going to be root 3 over 2, comma, negative 1. Alright, you'll notice there's a blank unit circle to the right. The reason there's a blank unit circle to the right is because you could do this exact same unit circle with all those points, but you could also do radians instead of degrees. So I'm just going to fill out what the radians would look like. This used to be 30 degrees. That's the same thing as saying pi over 6 radians. The other one was 40 degrees. Same thing as saying pi over 4. The other one's 60 degrees. That's the same thing as saying pi over 3. Up here, we have pi over 2. Over here, we have 2 pi over 3. The other one's going to be 3 pi over 4. This one's going to be 5 pi over 6. 180 is just pi. Then we have 7 pi over 6. Then we have 5 pi over 4. Then we have 4 pi over 3. And you can figure out all these radians on your own. You just have to convert all the degrees into radians, which is, I'm just saving you the work by showing you what the measurements are in radians. We have 5 pi over 3 right here. It's 7 pi over 4. And then we have 11 pi over 6. If you look straight out at the x-axis, that would be 0 radians, or it would be 2 pi radians. So you've either gone not at all, 0, or you've done 2 pi, which means 360. Alright, how the unit circle works and why it benefits us. We can use the unit circle to help us measure things. So, for instance, we have this question here where it says, point P is at negative root 3 over 2, comma, negative 1 half. So I'm going to estimate where point P is. I'm going to estimate that it is, if I look at my diagram back here on my unit circle, negative root 3 over 2, comma, negative 1 half is down here. So I'm going to estimate the point P to be over here somewhere. Point Q is at 1 half, comma, root 3 over 2. 1 half, comma, root 3 over 2 is up here. So I'm going to estimate it up there. Point P and Q are 2 points on a circle. If an object rotates counterclockwise from P to Q, through what angle has it rotated? So it went from point P all the way around to point Q. They want to know the angle that that created. Oh, that's bad. There we go. Let's try that again. They want to know the angle that that creates. To figure that out, we're going to utilize our unit circle. So point P and point Q are both on the unit circle. Point Q, if we look back, was at 60 degrees. So we know that in here we had 60 degrees. Just to get to point Q. Let me do it. So to get to point Q was 60 degrees. To get to point P, if we look, point P was at 220, no, where is it? 210 degrees. So 210 degrees would go from here all the way to here. So we have a few options here. You're trying to calculate this angle theta. And all you know is that 60 degrees would get you from the x-axis to Q, and 210 degrees would get you from the x-axis all the way to P. So what I'm going to do is I'm going to figure out the distance from P, show this the angle from P back to the x-axis. To do that, I'm going to go 360 degrees, because that would be all the way around, and I'm going to subtract the 210 degrees that would have got me to point P. So if I was to start at the very beginning and go all the way around, that would be 360, but if I start at the positive x-axis and just go to P, it's 210. 360 minus 210 would give me this gap in here. By calculating that, I end up figuring out that 150 degrees is this gap in here. But that only gets me from P back to the x-axis. I want to get all the way around to Q. So that means I need to go another 60 degrees, which would get me from the x-axis to Q. So the final answer for this would be 210 degrees. Now, there's other ways you can calculate that. So if you see that logically another way, you can calculate it, then do it the other way. If you can't, and you have to do it the way I did it, that's fine. And if that was really hard for you, it's probably pretty confusing because it is hard early on. The best thing you can do is draw graphs and try to draw what you know from the unit circle. Alright, a more common example of what you're going to do is you're going to find things called exact values. So they're going to start giving you angles, and they're going to say, what's sine of this? What's cos of that? We're going to do a few together and see if we can't draw some conclusions about what sine and cos tell you. So, sine of pi over 6. If I was to put sine of pi over 6 in my calculator, I would have to be in radian mode, because pi over 6 is a radian measurement, not a degree measurement. So I change it to radian mode, and I go sine pi divided by 6, and it tells me it equals 0.5, which is the same thing as saying 1. If I think about this for a second, pi over 6 is on my unit circle. Pi over 6 would have been right here. So if I was to calculate that by hand, sine would be opposite over hypotenuse. At pi over 6, the same thing as 30 degrees, so that would be the same thing as this triangle over here. Opposite divided by hypotenuse, opposite would be 1/2. Hypotenuse, because its unit circle is always 1. So that means sine was really just the y value on my unit circle at pi over 6. If I do it again and I look at sine 60 degrees, and I put that in my calculator when I'm in degree mode, sine of 60 degrees doesn't give me a nice number. It gives you 0.866025238. So that's an ugly number, not an exact value. That means to figure the exact value, there must be another way to do it. The other way to do it would be to use your unit circle. Anytime you see exact value, that means that you should be able to do it without your calculator doing the actual work for you. So exact value is a big hint to use your unit circle. If you look at your unit circle, 60 degrees is up here, 60 degrees. Here's my x and my y value. That means on my triangle, I'm going opposite divided by hypotenuse. The opposite is root 3 over 2. Root 3 over 2. And my hypotenuse is 1. Root 3 over 2 divided by 1 is still just going to be root 3 over 2. What you should be noticing is that sine gives you your y value from your unit circle. So this next one, sine of 45, without calculating it, I know it's root 2 over 2. The reason I know it's root 2 over 2 is I look back at my unit circle, I look for the 45 degrees, which is right here, and I know it's just my y value for doing sine. My last one, sine of 120, I want you to try it on your own. If you do it on your own, you should be looking at your unit circle. You should be looking at where 120 degrees is, and you should be looking for your y value, because sine gives y value. That means root 3 over 2 would be my final answer. On the bottom, we're going to do cos. Our hint for cos would be thinking about our sine. So if sine was opposite over hypotenuse, and hypotenuse was always 1, cos is going to be adjacent divided by hypotenuse, which is going to be x. So sine gives y value, cos gives x. Green doesn't help. It says cos gives the x value. So for cos of pi over 3, I'm going to look at pi over 3 on my unit circle. I'm going to look at the x value. I'm going to find that it's 1/2. Just for reference sake, I look for pi over 3, which is the same thing as 60, same triangle, and I'm looking for my x value, which would be 1/2. We can reach through these pretty quickly now. So cos of pi over 4, I'm looking at my unit circle. I'm looking for where pi over 4 is. And I'm just taking the x value. Cos of 90, I look at my unit circle for where 90 degrees is, and I take my x value. For cos 3 pi over 4, I look for where 3 pi over 4 is on my unit circle, and I take my x value. My last one that we're going to do is tangent. So tan is opposite over adjacent, which in our case, the opposite was always just your y value, and the adjacent was always your x value. So to find your exact value, you're going to have to look at your unit circle and go y value divided by x value. At 30, that means I would have y value of 1/2 divided by my x value of root 3 over 2. If you simplify that, you're going to kiss and flip it, and then you're going to rationalize it, you get root 3 over 3. We did that earlier. It was one of our special triangles. So if you don't remember how to do the math on that, go back to your special triangles. And you see we did it at the top of the screen up here. Remember, these special triangles created this whole unit circle. All right, for tan of 120, I'm going to look at my unit circle. I'm going to look for 120. I'll look at my unit circle, and I find 120 is all the way out here. There's my x and my y values. I'm going to go y over x, because that's opposite over adjacent. So I have root 3 over 2 divided by negative 1 over 2. You simplify that properly, try it on your own, and you end up with negative root 3. For tan at pi over 4, I look for pi over 4 on my thing. I find pi over 4 is at root 2 over 2 and root 2 over 2. So y divided by x would be root 2 over 2 divided by root 2 over 2, which just equals 1. My last one's my hardest one, so I have tan of negative 4 pi over 6. That means we need to go backwards, 4 pi over 6. So you're going to have to like really think about what that means. Sorry, I left my units right there. I want to go backwards 4 pi over 6. Well, I know if I went forward 4 pi over 6, that would take me to, oh, that's a mean one, 4 pi over 6. Is that what it was? 4 pi over 6 simplifies. 4 divided by 6 is really 2 pi over 3. So if I look back at my unit circle, that's why you probably couldn't find a 4 pi over 6 if you were trying it on your own, because it simplifies to be 2 pi over 3. If I look at this, I see 2 pi over 3 is right here. That angle right there. But this is negative 2 pi over 3. So I need to go backwards that same distance to here. That would be our angle of negative 2 pi over 3. That means my x and my y value are down there at that point. So you're going to have to think about it if it's positive or negative, and that takes a pretty good understanding of angles from lesson 6.2 and understanding how to go backwards and things. Anyways, if you look at your unit circle down there, you have a x value of negative 1/2 and a y value of negative root 3 over 2. You're going to go y divided by x, negative root 3 over 2, divided by negative 1/2. The negatives will cancel out. If you kiss and flip it, you end up just getting root 3 as your answer. So this means our primary trig ratios. If it's on the unit circle, sine equals y, cos equals x, and tan equals y over x. That's the big thing that you need to pull out from today. You need to pull out how to read the unit circle, and you need to pull out that sine is the y value on the unit circle, cos is the x value on the unit circle, and tan is y divided by x on the unit circle. If you want to try this question on your own, we'll go over it in class, okay? So on Monday when we come back, we will look at this one on our own, and we'll investigate what it means. This would be an extension, so it would be a challenger question, maybe a standard of excellence question on a unit test.